Hi, Professor.
Hi,
Yeah.
Professor.
Hi.
Hi
Good
there.
afternoon. Good afternoon. How's everyone? So someone said hi everyone, and in the chat box, nobody was nobody was greeting back.
No,
Um,
Professor, you came late. We were talking the whole time.
Yeah, yeah, yeah.
yeah. No, I came in, like on time. It's just, my microphone. I had to unmute my microphone, and I have to adjust a little, some settings a little. Okay, good thing that you guys were, greeting each other before I, well, emerged, because, until I turn on my microphone and adjust some settings, it's not quite visible. So, okay, so I'm sharing my screen. It's always taking some time. I gotta get a new computer. And this one, okay, so my screen is being shared now. And so um, we were, let me also open, where was this thing? Hmm, Okay, I'll have to, let's go out to. So we were talking about how to solve for um, rate, right? In our last class. Oh, where is it? Modified six. Where is that thing? Time value of money. Well, I have. So yesterday, yeah, here. So and so there are four variables in the base formula in base compounding. Um, okay, why? Okay, let me try this. Is it frozen? Why is it not? Hmm. Oh, okay. Now there it is. But okay. So the base formula for compounding is this: basically finding future value, right? From this, uh, we derived the formula for present value and formula for R, right? The formula for present value is, of course. So it's like reverse engineering. I mean, if you all understand what reverse engineering is, um, it's like backtracking, right? Um, so, and each of these, variables can be the unknown. First, future value was the unknown, but then if principal is the unknown. And then, of course, the rest of them are known. And then if R is the unknown, we know uh, that's, and then you might remember from before. Oh no, this is business 210. You don't remember this from before. I just got confused because 6 o'clock I have another class, Finance 100. um, okay, so then our next question is, what if n is the unknown? In other words, yeah, we can think about a scenario like that. Of course, you have 10K principal, you put it in the bank, and currently APR is, let's say, 10%, and you have a target future value. So you want to grow it to 50K. Our next question is, so if the interest rate is 10%, how long will it take? How long will it take to grow your 10K to 50K, right? Of course, it will take a long time because even if APR is 100%, if you think about it, if the return is 100%, every year it will double. I mean, it will actually more than double because this is compounding. But even in simple interest, even with simple interest rate, it will be it will take, if it is 100% every year, it will take 5 years with, simple interest. But thanks to compounding, it will take less than 5 years. But, n, question is, n, so how many years, or it could be how many months, how many years, but, eventually, depending on what the compounding frequency is, in other words, depending on whether we use, annual compounding or monthly, quarterly, semi-annual, daily, depending on the compounding frequency, right? Whatever this may be, right? Then, n will be determined. I mean, if it is, if this is 12, right? If m is 12, n will come out as months, then we can convert it into years. It's not a difficult thing. It can be quarterly, and then, whatever. So then let's think about how we can solve for that. Now, so first of all, it is pretty much the same thing if you think about it. Starting from the base formula, right? From here, now everything else is known, but the only thing, n is the unknown. So how do we isolate n? First of all, we can isolate, as far as we can isolate, right? Fe over P, that's the first thing, and then we have 1 plus R raised to n. Now, so now we are back into, we're back to z equals x raised to y structure, right? We're back to z equals x raised to y. And then when we have that structure, how do we isolate the exponent and how do we solve for that? Now to to understand that and to be able to do that, you need to understand log or logarithm, right? So what's a log? And this is something you learned, in middle school or high school. And if you've done, if you've taken math on a college level, algebra, this is something you have already encountered. It's nothing new. But then, some of you, this is the first time you've ever, encountered this. And in the U.S. public school system, they hardly push, science and math and science. Some schools do, but most public schools, they don't. They just, reading and writing is the highest achievement from K through 12. That's really disappointing. I mean that's appalling even. But anyway, so I need to explain all of this all over again. So basically, log is a way of expressing a large number by the exponent of some base number. Okay, so what that means is basically we all know 100 can be expressed as 10 squared, and then 1000 can be expressed as 10 cubed. And this way, moving this way, 1 million can be expressed as 10 raised to the 6th power, right? And when you do this, this is base, right? 10 is the base. Of course, the exponent. Now, we can write these numbers again. We can write these numbers like why is it there? First of all, we can express in log. Log is basically using 10 as the base. 100 log of 100 to base 10. The way you read it is there are a couple of ways. One, base 10 log of 100, right? Because it's log based with the base of 10. Base 10 log of 100, or log of 100 to base 10. Log of 100 to base 10. And of course, we can rewrite this as log of 10 squared to base 10. Now, basically, log of 10 to base 10 is 1 because it's 10 itself, right? And the exponent, when you 10 is 10 to itself, 10 raised to 1. It's just itself. So log of 10 squared to base 10 is basically 2, because it's 2 times log of 10 to base 10. In other words, when you express the large numbers in log to the base of some number, right? You can move this. You can move the exponent down so it can it looks like x times y. In other words, multiplicative uh, function. In other words, previously it was a power function. This, I've been telling you, this is called power function because it's powers, right? Powers of 10. Now, you turn power function into multiplicative function, right? Using log. Okay, so, and then we know log of 10 to base 10 is 1, so it just turns to 2. And by the same analogy, right, by the same, or by the same method, if I lift finger, then oh, I didn't lift a finger. I didn't lift a finger, and still that eraser is gone. That's okay. So then, see, that way, 1,000 will be, we know 1,000 is log of 10 cubed to base 10. And then this will be 3 times log of 10 to base 10. So it becomes 3. And 1 million, that's log of 10 to the 6th power to base 10. Then it becomes 6. Now, not all the numbers can, the examples I've given you is called common log. Okay, and the common logs are very easy to understand because everything is powers of 10. I mean, we can easily convert 100, 1,000, 1 million, 1 billion, 1 trillion into powers of 10. So it's 10 to the 6th, 10 to the 9th, 10 to the 1 billion is 10 to the 9th. 1 trillion is 10 to the 12th. In other words, it's exactly the number of zeros, right, after 1. But so common log is easy to visualize. It's easy to envision. But then not every number can be is amenable. Not every number is amenable to a common log. I mean, think about it. A number like 13 or 17, or even 1.7582, you cannot. I mean, it's not impossible. You can take the common log of those numbers, but it's hard to visualize those numbers, right? It's hard to even visualize what it can be. But then the next question is, then why do we use log? Because think about it. We have, let's say, we have a physical distance, like between the Earth, let's say the distance between the Earth and the Sun, like this is our Sun and Earth. Let's say the distance between the Earth and the Sun is, I mean, just for the convenience sake, let's say 1 billion miles. 1 billion miles. That's 10 to the 9th. Or just for convenience sake, let's call it 10 miles. Okay, 10 miles. It's obviously, we all know that's out of the question. I mean, that's just impossible. But let's say it's 10 miles. It's 10 miles. Then let's say the distance between the Earth and the nearest galaxy, it would be like, I think, 8 light years or 80 light years, the nearest galaxy. That means, 1 light year is like, I don't know, 1 light year is like 80 billion miles or whatever, 80 million miles, or that would be a huge distance. I mean, 10 light, even if it is a 10 light years away, right? And how would you express that? Of course, on it's going to be very difficult to show it on a viewable space, right? Even if you have a huge, screen, um, with the, if this is 10 mile between, Earth and the 10 light years away will be like, 80 million times, or 80 billion, 8 billion times, whatever, let's say if it is 8 billion or 100 billion miles, 100 billion miles. 100 billion is, so how can you express it? How can you condense it into I mean, 100 billion is, 10 billion times 10 miles. I mean, you should have, even if you have only if you have an infinitely stretchable screen, then you can express it on it. But then, drawing that line over such a, infinitely stretched screen, it will take a lot of time, and obviously, you cannot hold the attention of the audience until you. So the easiest way, then, the easiest way is using the log, because if, again, if this whole distance is, like 100 billion miles, which is, think about it. 100 billion is 1 billion is 10 to the 9th. So 100 billion is 10 to the 11th, right? 100 billion is 10 to the 11th power. So if we use logarithmic scale, normally you will think, oh, this is 1, this is 2, then 2 is 2 times 1, 3 is 3 times 1, or in other words, 3 means 30 miles, 4 means 40 miles, 5 means 50 miles. No, that's normal scale. But if we use logarithmic scale, then 1 is 10 to 1, 2 is 10 squared. So 2 means, 100, 3 means 1,000, right? 4 means 10,000. So this way, when 6, 7, 8, 9, 10, 11, this point is 100 billion miles, right? In other words, this is basically condensing. It makes our job easier, right? This allows us, logarithm allows us to condense a huge quantity, a huge quantity, or condense, or make it compact, right? Condense a huge quantity into a manageable scale, on a manageable scale, right? Manageable scale. So that's what the log does, right? Of course, that's not only, it's just one example. I'm showing you just, so that it can be easily, and then there isn't only common log. Actually, most commonly used logs are 3. There are 3 logs three bases. In other words, three bases for logs. Three types. One, common log, right? Of course, which uses 10 as the base. So that's log of x to base 10. Second one is called binary log. Binary is 2, right? So log of any number to base 2. And binary system is quite useful. A binary system is the basis of computer science, basically 0 and 1, 0, 1, 0, 1, 0. So if we use binary log, right, basically 4 is 2, 8 is 3, right? 16 is 4, basically. And then the third one is natural log. Natural log. And the natural log is based on Euler's number E. Now this is quite a heavy, topic because Euler's number. First of all, what's Euler, or who's Euler? And Euler was a German mathematician, sometime around 1600 something, or so that's 17th century or 18th century. Of course, long dead. But if you want to name two modern, if I have to name two modern mathematicians that made a great impact to the modern math and science, are Gauss and Euler. And they are both like Swiss Germans. So some people call it Euler, but then I don't really like that, because because it's been called Euler ever since. So not only because not only out of respect for his heritage, but if you suddenly call Euler's number, that's but anyway, because Euler discovered this. What is Euler's number then? Euler's number is basically something like this. So let's say we know what M is. M, right? Compounding frequency, right? So, and we think we know compounding frequency is 1, 2, 4, 12, right? 52, 365. But I told you it can be even. I mean, this is daily compounding, but I told you it can be even by the second. But is there any way we can stretch it to? What would be the highest compounding frequency? Well, the highest compounding frequency is, of course, infinity, right? So think about it. If we split 1 year into 365 pieces, that's daily. And then if we divide it by 365 times 24, that's by hour, once again, then times 60, then by the minute. So the higher this compounding frequency goes up, we're splitting time into infinitely small fragments, right? And if you imagine, if you are looking at the data, I mean, we have, let's say, I have collected your height data. I mean, let's say I know one of you from your birth. So every year, at the end of each year, I measured your, of course, at the age of, so this is the timeline. 0. At the age of 0, you still would be, how tall would you be at 0? When you were just born, you would probably be, like 6 inches. But, from there on, every year, at the end of every year, I measure your height. Over the years, right, it will be plot. It will be a plot, right? It will be a plot. Some years, more. And if you connect those plots or dots, right, it will be not a very smooth curve, but just, straight. It's not a straight line, but, kinked lines. There are kinks here, kink here, kink here, kink here, right? It's not smooth. But if I split it into, but if I measure the heights like, monthly, it will be smoother than this. If I split it, if I do it by weekly, it will be smoother. If I measure it by daily, it will be smoother. In other words, when something is growing, right, if I make the observation, the more frequent I make the observation, in other words, the more into more fine fragments of time, into more finer fragments I split the time, the data can be, the data plot can be smoother. It will be smoothed out. So it can really reflect the growth over time in reality, right? The real growth over time. It can emulate the real growth over time. So, so that's the idea. That's why, if we when we use, daily compounding, it will give you more, greater future value. I mean, whatever you so basically, by splitting time, by using higher frequency, then we will get a smoother path that looks more like reality. So that's why we want to increase it. But the maximum we can increase that to is, of course, infinity. We can raise it to infinity. But then let's think about it. In the formula, right? So that's why we are splitting APR by M, and then within 1 year, just within 1 year, right? There will be, let's say, so T is 1. So then, we want to focus on, okay, of course, there was P here, right? There is P here. I forgot to put P there. P times, right? But we want to focus mainly on this. So I'll take that out, and let's think about. Erase that. And then let's think about M going to infinity. If M goes to infinity, let's say this is infinity, right? And this will be infinity, right? And assume APR is 100%. So in other words, if we can double our money every year, right? Because 100% is 1, and later we can just simply switch that 1 with any number, right? For now, we'll just assume APR is 1 or 100%, then this will look like, you know, 1 plus 1 over infinity raised to infinity. Now then our question is, what's this going to be? What is this number going to be? That's an interesting question, isn't it right? Why? First of all, if this number is, what's this number going to be? 1 divided by infinity. If you divide 1 by infinity, what do you think? Anyone? What do you think the number is going to, what's it going to be like? Anyone? This is a 1-point question, if you answer it, of course.
It's going to be an infinite number.
Infinite number. No, but then what is an infinite number? Infinite number means a very large number, infinitely large number. Isn't that right? Infinite number is an infinitely large number. But how can you arrive at an infinitely large number? Don't type in there, because as you can see, I cannot see whatever you type in there. Because
Harold said undefined.
Undefined. Okay, that's closer. But logical reasoning, think about it logically. If you divide 1 by infinitely large number, it cannot become infinitely large. It will be infinitely small. Isn't it right? Divide any number by infinity. Infinity means infinitely large, right? If you divide 1 by 10, it will be 0.1. It becomes smaller. If you divide 1 by 100, it will become 0.01. If you divide 1 by 1 million, it's going to be 0.0006 zeros and 1. So if you divide by infinity, it will become infinitely small. Infinitely small, there's a word for that, infinitesimal. Infinitesimal means, infinitely small. It will become an infinitely small number, almost close to 0. Think about it. Infinitely small number is, I mean, if it doesn't become 0. It's not exactly 0, right? 0, the only thing, 0 divided by something is 0. But you cannot divide 1 by 0. Anything by 0, it's undefined. If you divide 1 by 0, anything by 0, it's undefined. Now, if you divide 1 by infinity, it will become an infinitely small number. So that means close to 0, but it's not exactly 0. Right? Then think about it. If this thing is 0, completely 0, I mean, if 1 divided by infinity is 0, problem solved. It's a very simple question, because if this thing is 0, the whole thing is 1, and then 1 raised to infinity. What is 1 raised to infinity? Anyone? What is 1 raised to infinity? It's just logical thinking.
Professor, I have a question because I'm kind of confused.
Okay.
So if zeros mean that it's like empty, it's nothing there to come. Undefined.
Yeah.
So did you say that?
Again?
Did you say that 0, right? The definition of 0 is something that doesn't have a value that you can account. And you're saying basically the same. So what is the difference between undefined and 0?
I'm undefined and 0 are two different things. 0 is defined. Undefined is undefined. Right? Look, this symbol is not equal to 0. You understand? This symbol is close to, okay? It's not 0. It means approximately equal to. That means approximately equal to. You understand?
Yeah.
That's not equal. So it is close to 0, but not 0.
Okay.
Undefined means we don't know what it is. It cannot be defined. But in
Um,
this case, yeah,
can you give me an example just to clarify? Because I'm still a little bit confused.
okay. Uh, 0 divided by anything is 0, because if you divide anything, 0 by anything is 0, but 0 over 0, that's undefined. That's because there's nothing, 0 is nothing, you cannot divide nothing by nothing. So that's undefined. I mean, and um, uh, also, what else? Something like 0, something like this, x divided by, that's undefined because you cannot divide anything by 0. There's no way you can divide it because 0 uh, has 0 is nothing. You cannot divide anything by nothing. Now, in this case, I said undefined is close, but it's undefined is close, um, but not exactly uh, not exactly the thing, because it it has um, it has some limit. We reach some value in limit, but which is very, very, very infinitesimally small number, close to 0, right? But it can be defined, right? Um, so again, if this thing is 0, right? If 1 over infinity is 0, then problem solved. And my question was, so if this thing is 0, you see, if this thing is 0, what will be the whole thing? In other words, if this thing is 0, 1 over infinity is 0, then the whole bracket is 1. If you raise 1 to infinity, what's it going to be? Think about it. Raising 1 to any number, I mean, what is 1 raised to infinity? The answer is obvious. Isn't it right? Try 1 times 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 infinitely. That's 1 raised to infinity. But then what is it? 1 times 1 times 1 times 1 times 1 times 1 infinitely. What is it?
Is it 1?
Yeah, it's still 1, of course. Think about it. That's just logical thinking. And who was this? Who
That's
said that?
Dennis. Dennis.
Okay, Dennis. Okay, Dennis, I'll give you 0.5 for that.
You said it's a 1 point question.
Did I say it was a 1 point question?
Yes.
Probably 1 point question was 1 plus 1 over infinity raised to infinity. I believe that was. Okay, so I'll give you, anyway, I'll give you 1 point. What's today?
Thank you.
28. Okay, you're welcome. It's just logical. I mean, it's not math. There's no calculation. It's just logic, isn't it right? It's of course math. Math is logic. 1 raised to infinity, 1 times 1 times 1 times. You do it infinitely, still 1, right? It's just logical thinking, but a lot of people just turn catatonic when it comes to logical thinking. Hmm? Not
So
just, logical thinking is just, give me a second. Logical thinking is nothing but pausing for a moment and really, give your thinking a structure, right? Literally, because 1 raised to infinity, oh, what is raising to some power? It's like, if it is 2 squared is 2 times 2. 2 cubed, 2 times 2. So 1 cubed is 1 times 1 times 1. 1 to the 10th is 1 times 1 times 1 times, 10, like that, 10 times. And 1 to the infinity, 1 raised to infinity is 1 times 1 times 1 times, infinitely, right? Again, but then,
Professor, I'm sorry, it's just I'm still a little bit confused because I mean I understand what you mean, but I'm in another class I learned that one raised to infinity is undefined, and I'm just
no,
trying to.
1 raised to infinity is 1. 0 raised to infinity will be undefined. Think about it. I mean, use your logic. 1 times 1 times 1 times 1 times 1 times 1 times. You do it no matter how many times, it's still 1. Use your logic.
So I put a definition that I found. Can you just clarify a little bit? It's just I want to understand, because I feel
Hold
um
on. Okay. Let me finish this. Let me finish this first. So if 1 over infinity is 0, problem solved. I mean, it's an easy question. However, as I said, 1 over infinity is not 0. It is infinitesimally small number, and so it's close to 0, but not 0. So in other words, 1 plus 1 over infinity is something slightly greater than 1. It's like 1.000000000000000 infinitely 0 and 1. But then the question is, if you raise something like that, if you raise that to infinity, what's it going to be? If it is 1, it will still be 1, but it is like 1.0000000 infinitely 0, and you raise it to infinity. It's not going to be 1. It's not going to be 1. It will be close to, actually, if you do that, you will be surprised. Uh, it comes to something like 2.718 something something. It's an irrational number. It goes on forever. 2.71818 blah 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 blah. Just like pi, it goes on forever. And to 3.14 something something, they gave name pi, just like that. They gave this, what is it? They gave this the name E for Euler, because Euler discovered this, right? Okay, so then um, I will. You can experiment that. I will show you. Uh, so then, natural log is what? Natural log is the log using Euler's number as the base, and we write it also. So it's log of x to base e, or we write it like this: ln of x. So of course, ln, what would that mean? Natural log. Okay. Now, Harold, that was Harold, right? You had a
yes,
question?
yes, that was me.
Yeah. So what is the question now?
It's in the chat.
It's in the chat. Uh, how much is 1 to the power of infinity? The 1 to the power of infinity is 1. It is 1. It's not unknown. It is 1 times 1 times. No matter how, no matter how, look, you write it like this. Okay, 1 to the Okay, infinity symbol, I cannot find it on my computer, but okay, I better show you using uh, raised to negative infinity. That can be undefined. Look, because raised to negative infinity, it means 1 over 1 over infinity, and that was already discussed. We already talked about that. If you write okay, using why isn't it okay, if you put it into Excel, and I've been telling you, this is the universal machine language for raising something to power. So you write it like that's 1 raised to infinity, right? But of course, to human eyes, 1 raised to infinity. What is 1 then? So this is 1 times 1 times 1 times 1 times, but negative. Look, that's 1 over infinity.
Yeah, now I got it.
Okay.
Yeah,
Then it becomes an infinite. It's undefined because it's become uh, it's like 1 divided by 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 1 divided by, right?
yeah.
It's just logical thinking. Now, so where was I? So that brought us to natural log, understanding of natural log, and then one thing good about natural log is one thing convenient about natural log is um, uh, with natural log you can take log of any number. I mean, it's natural log of, let's say, 1.00735, or you can take natural log of any number, 17.217, or in other words, common log. Yeah, yes, you can take the common log of numbers like that. I mean, it's not impossible, right? You can take common log of, something like this still, uh, because it's the calculator that will calculate it. But it's just hard for human brain to envision what it might be, right? Um, you can take binary log of any number, but still it's hard to envision it unless it is like powers of 2. And with common log, unless it is powers of 10, it's hard for human brain to envision. um, but with natural, and the reason the natural log can take log of anything is because it's based on a number that is infinitesimally, it's just slightly greater than 1, based on the number that is slightly greater than 1. And again, if it is 1, it's pointless. You cannot take log of any number to base 1, because 1 um, uh, see, no matter what you raise, what you raise 1 to, it will just be 1. So it cannot be the base of any log. But if you use a number that is slightly greater than 1 as the base, uh, in other words, the whole continuum of numbers can be amenable to taking log. Okay, so then all that How does that solve our problem? In two ways. One, because remember we have that. No, go away. We are stuck here. In other words, we have FV over P equals 1 plus R raised to N. It can help us in two ways. One, first of all, by taking the log, if we take log, and again, we can bring this down. In other words, what used to be a power function, x raised to y, what used to be the power function can turn into a multiplicative function now. In other words, if we take log, and when you take the log, you have to do the same thing on both sides. You remember when you have an equation, because this equal sign means whatever you do to the right-hand side, you have to do the same to the left-hand side. Otherwise, equal won't hold. So you will take log of the right-hand side, log of x raised to y, and you do the same in the left-hand side. And then this exponent can be brought down just like as if it is the coefficient. You know that is x, as if it is the coefficient, right? And then this becomes exactly, once again, z equals x times y structure. It becomes, once again, z equals x times y structure. And then y is our, unknown. So then we can solve for it. It's this y, right? So which is, this one, right? We can solve it. Z divided by y will give you x. That's one thing. By taking the log, we can turn the power function into a multiplicative function, which can be, and then second, so let's take the log, and then we have to take the natural log, because why? Because we don't know what these numbers will be, right? They may not be amenable to a common log. Even if you take the common log, it can, the computer can calculate it, but it's hard to envision for human brain. So if you take the natural log, and it's an abbreviation, right? The thing in the bracket, right? The thing in the bracket. So then the whole thing will become natural log of the thing in the bracket equal to n times the natural log of 1 plus r. Now we can solve for n. Isn't that right? We can solve for n. Right? Then n is simply natural log of the thing in the bracket, which is FV over P, divided by, okay, I'll have to, I just lift a finger for a second and then the eraser is gone. Oh, where is it now? Again, I didn't close it. I hope it is still there. Okay. So, and then, where is it? So divided by natural log of 1 plus r. Now we have the formula that can solve for n, right? Good, everyone? Now we can go back to our, so then now we can go back to our Excel. Okay, here it is. I guess I can close this now. Okay, So that's the formula there. And also, let me see. Uh, um, time value of money. Where is it? Time value of money. Okay, let me sort it by type. Where is it? I don't see T. What happened? I thought I had it. Was it compounding? I think it is this one then. Yeah. So here you see, okay, here is the formula for, okay, where, come on. Now this is the steps of derivation, right? You see, this uh, this is the steps of derivation. From this, you arrive at this. Of course, if you can understand this process, and if you can remember and emulate this process, that would be wonderful. But even if you don't, I don't blame you. I mean, even if you just remember the final product or the final outcome, it's already good. But again, instead of memorizing, because if you memorize it after the semester is over, you forget it all. But if you understand the process, you can always derive it from the scratch, right? From the base formula. Uh, but again, I won't blame you even if you, okay. So if you go back to our problem, our example, okay, I think it's because we're gonna do this, and we understand, we know the answer, right? Because it's the same example we used yesterday. So it will have to be 5 years. We will have to, we'll check if it comes out as 5 years, okay? But it's 4:05 already, 4:06. So I think it's a good time to take a break. So let's take a 10-minute break and reconvene at like 4:15, 4:16. Okay? All righty, let's take a 10-minute break. All right, we're back. We're back. So where was I? Yeah, now we are ready to solve solve the problem, solve that example for n. So here, okay, yesterday I had. Uh, um, so everyone is with me. Hmm? So let's do this.
Yes.
Okay, good. Let's do this. Um,
Yes.
so row 23, we know it's 5 years, but let's see if it's gonna be really. I mean, if we get 5 years by using this formula, then it checks out. Our formula checks out exactly. Okay, so and we're gonna ignore m for now because it's when m is 1, it doesn't make any difference, right? So we're gonna take the natural log. You just enter ln, right? Of fv over p, okay, divided by natural log of 1 plus uh, APR, right? And it's gonna give you exactly, and hit enter. Hit enter and tell me what you got. And I know, even without hitting enter, I know I'm going to get 5. If you hit enter, yeah, I got 5. Everyone got 5? How do I double click? Everyone got 5?
No, Professor.
No? How come? What did
Yes,
you
I
get?
got 5.
Of course. And don't bother with the uppercase, lowercase, because even if you don't waste your time capitalizing, um, using caps, key, or even if you enter in lowercase, it will automatically turn into uppercase, so you don't have to. Alrighty, so we got it. Next one, row 25. Now this time compounding is quarterly. Quarterly. And of course, when compounding is quarterly, it takes smaller APR to arrive at the same target future value. So we know the answer already. Ah, come on, go away, go away. If so, given 22.59% APR, we know the answer will be still 5. It's going to be 5 years. But we'll need to make adjustment for that compounding frequency. So anyway, we're gonna do natural log. We're gonna take natural log. We'll have to start with the equal sign. Natural log of FV over P divided by natural log of 1 plus, this time, think about it. Compounding is quarterly, so this APR will have to be adjusted by M, right? So in other words, we are using periodic rate, and then what we will get initially, what we are going to get will be quarters. How many quarters, right? So it's going to give us 20 quarters, but then we will convert it into years, okay? So we divide it by M is in D25, so that's in D25, and hit enter. And I told you, this 20 is not years, 20 years, but 20 quarters. But look, you cannot leave it like this because the label is years, right? Time is given. So then you have to turn it into years. So what do you need to do? The whole thing, because this whole thing gives you 20 quarters, you'll just need to divide it by M, which is in Again, D25. Okay. Now, you can take screenshot of this, right? Because later, just like yesterday, you might want to know, right? You can take the screenshot of this. So now I'm gonna hit enter. Then it's gonna obviously, yeah, we know it's gonna be 5 because think about it. From here to here, it's 20. From here to here, the result of that is 20, and then you divide it by 4. It will have to give you 5. So hit enter. Yeah, 5. Right? So it all checks out. Again, it is. We want to take a simpler model, right? We want to take use the simpler model. That way, it's easier to fix the problem. If there's any error, it's easier. It's easy to fix problem.
Professor?
Yes.
Hi, this is Shirley. I want to. Can you please explain again why you changed it to 20 if it was 5 before?
Yeah, because I didn't change it to 20. It was, look, it comes out as 20 because we are using M is 4. In other words, it's quarterly compounding. So the rate had to be adjusted. This is annual, so we had to turn it into quarterly rate. This gives you quarterly rate, isn't it right? APR divided by 4. So then when you use the quarterly rate, it will give you quarters. It will give you time in quarters. Right? Then when the time is given in quarters, then you need to convert it into years because the problem is asking for years. Time in years, right? Okay, did that answer the question?
Thank you.
All right. So there you go. Then 5. Now let's do it. Go to row 30 and let's use a simpler model. So just like yesterday, we're gonna turn it into we have 2 more columns. The column for R, the periodic rate, column for N, the actual number of compounding. So then this will be the ultimate answer. But first, we will need to know what is the periodic rate. So we'll just divide it by annual rate divided by 4. That will give you, yeah, of course, we know it should be 5.65. Now then we're going to find natural log of FV over P divided by natural log of 1 plus R. We used periodic rate, so it will give us, we use quarterly rate, so it will give us quarters. How many? 20 quarters. Then we convert it into years by dividing that 20 quarters by 4, and that gives us 5 years. Okay? Everyone got the same result? Come on, answer me. Did you get the same result? Okay, good. Okay, good. Okay. Now I just want to revisit. I mean, this was what infinity issue, right? Infinity. Yeah. I was a little, mistaken. I mean, first of all, 1 raised to infinity, 1. Of course, because 1 times 1 times 1, 1 times 1 times 1 times 1 times 1 times, infinitely, still 1. 1 raised to negative infinity, it's uh, uh, just momentarily I mistook it for 1. Okay, it's actually 1 over 1 raised to infinity, right? So it will still be 1 because think about it. 1 over 1 times 1 times 1 times 1 times infinitely, still 1. This thing is 1, right? So 1 over 1, it will still be 1. And you can check it because on Excel, I already did it. Here, um, how do you put infinity in Excel? This is infinity. This is how, I mean, symbol infinity, you can, from Word, you can find, word symbols. You can, also, I guess, from symbol, you can find symbol here. You can enter symbol from, but, actually how you enter infinity in Excel, it's raised to, this is infinity, 1e plus 99. It's like, a lot of zeros. And then negative infinity, that's how you do it. Still, it gave me 1. I mean, you can check it out. Okay? How do you then, like a label, for label, how do you enter infinity? For label, you can, I don't know if you, insert, there's insert, and then there is, you can insert uh, objects, like, and then, symbols. But I don't know. This is online version. I don't know if that gives me that insert. It doesn't give me a symbol. But from Word file, you can also insert. You can go to symbol, and you can find infinity symbol there. But it's not really important. That was also done here. So you see, I was able to find infinity symbol from my Windows computer, and I entered it here. It's just right. Okay, so that brings us to that concludes single cash flow model. Now, single cash flow model is where is my okay. You may have noticed that I use, in the bottom tab, I use SCF, MCF. That stands for single cash flow. Why is it single cash flow? Look, we are doing like, finding future value. There we get, so first of all, there should be single cash outflow from you. Isn't that right? I mean, when you deposit $10,000 in the bank, when you put 10,000, it's cash outflow from you. Isn't that right? Cash goes out from you. So cash outflow, and just single deposit, single cash outflow, and 10 years later, there will be a cash inflow. Isn't that right? You get it? So the money leaving you, that's cash outflow. Money coming to you, that's cash inflow. There's a single cash outflow and single cash inflow. Isn't that right? When you put $10,000 at 10% for 10 years, 10 years later, you will have like, $26,000. That's single cash inflow, right? That comes back from single cash outflow of $10,000 10 years ago or 5 years ago, whatever. So that's called a single cash flow model. But that's not the case all the time. Why? Because sometimes you make multiple cash outflow. I mean deposit. So what would be the? Let's take a look at the example. The example is here. Hmm, hmm. Okay. Uh, Multiple cash flow compounding. Uh, One example is a annuity. One very good example is annuity. What is an annuity? So here, let's take a look at this example. So suppose you are preparing for graduate school. Okay, so you start the graduate school fund. What's the like college fund, and then so you are thinking of going to CUNY graduate school, right? MBA program at Zicklin, or it doesn't have to be CUNY. You can go to Columbia, or you can go to NYU. You can go to Fordham, or you can go. But other these schools are very expensive, right? CUNY is the most affordable school. Because if you go to Columbia and for NYU or NYU for especially NYU for MBA program, it will cost you at least like $50,000 to $60,000 a year, maybe $50,000 a year, maybe not 60,000. Why? I mean, undergrad programs are more expensive because NYU and Columbia, maybe not necessarily, but let's say you go to Princeton or Harvard or Yale or MIT. Why? Because of the residence. In other words, dormitory. Most of the large chunk of the tuition is not just tuition for for class, but a lot of it is room and boarding. Room and boarding, right? Meals, room and boarding. So if you have to, so usually Princeton, MIT, Harvard, Yale, Stanford, they cost like $60,000 a year. For 4 years, that's going to be $240,000. Now CUNY, being urban campus, there's no dorm. So at least you don't pay for room and boarding, just pay for the classes. So that's why it's more affordable. But still, graduate school would cost at least MBA program still about $30,000 a year, I guess, 30,000. So for 2 years, it's gonna take you 60,000. So how do you accumulate 60,000? So let's say you are planning to go to start MBA program in 5 years. So you're going to save $800 every month. So let's say you get a part-time job, and from this part-time job you can save $800 every month at the end of every month, right? So here, what do you see? There's a regular amount saved at regular interval. And quickly, in a quick thinking, you would say, okay, if it is $800 for 5 years, of course, first of all, you will have to graduate from college, and let's say that's going to take 4 years to 5 years. I mean, just to be on the safe side, you have to graduate with a bachelor's. So then, 5 years is 60 months. 60 months, 800. I mean, I'm sure it's 48,000. I know 800 times 60 months. That's 48,000. Just the principal alone. In other words, every 800. That's simple sum of that. So that principal alone will fall far short of the your target future value. Your target future value is 60K. So then, but with the interest, if they pay, let's say the interest rate is 6% a year, maybe with the interest it might get us there. Hopefully, but we don't know. But we'll find out. We'll see. So the idea is like this. This is a simplified version. This is the future value of annuity, but in this is very brief. The scenario is like this: you save $1,000 every year at the end of the year for 5 years. Then what's going to be the future value of all that? This type of cash flow is called annuity. Why? Annuity sounds like something annual, but it's not. It doesn't have to be annual. It can be quarterly. It can be monthly. It can be whatever, daily. But the important thing is there must be regularity. In other words, same amount at same interval, regular interval, right? Regular amount at regular interval. Then, and suppose interest rate is 20%. Now think about it. First deposit you made at the end of year one will be compounded 4 times, right? By the end of the timeline, 5 years, it will be compounded 4 times, and you come to this. Second one will be compounded 3 times. Third one will be compounded 2 times. Fourth deposit will be compounded just once. Last one won't be compounded at all because you make that deposit at the end of year 5. So actually at the end of year 5, you take the money out. So technically, you don't even have to deposit it. But for technicality, let's say you deposit it and just you dip it and just take it out right away. So it's not going to earn any interest. So if you add up all those future values, it comes to this, right? That's the idea. Now, our example is more complex than this because we have 60 months, so there will be 60 compoundings, right? Let's take a look. So our first deposit, so it's future value of annuity, and as I said, annuity is a regular payment or deposit at regular interval. And then think about it. First deposit, that's called payment. Payment and deposit are two sides of the same coin, right? If you borrowed money, you will have to make payment every month. If you are saving, it's deposit. So the first deposit will earn interest. And that interest is monthly interest. Isn't that right? Monthly rate, because you are, making monthly deposits, and so it's going to earn interest monthly. So if 6% is annual, you remember APR is 6%, you divide it by 12, all right? And the first one will be compounded 59 times, not 60 times. You understand? Why? Because you made the deposit at the end of the first month, not at the beginning. Okay? Here's that difference. Now, suppose you made the deposit at the beginning. Then there will be 5 compoundings. 1, 2, 3, 4, 5. Right? But you made the deposit at the end. So the first deposit will be compounded 4 times. Now, if you made the deposit at the beginning of the year, first one will be compounded 5 times, second one 4 times, right? And so on. Okay, you get the idea? And then the second, so therefore the second deposit will earn interest 58 times, and that. And there will be, then 59th deposit. I mean, 58th deposit will earn interest 2 times, right? The 59th deposit will earn interest just once. And the last deposit, 60th deposit, will earn no interest. It's just, just a payment or just a deposit. Okay? So this is, the idea behind it. I mean, if it is just 5 deposits, it's easy to put it on the timeline. But this is 60, right, from 0, 1, 2, 3, 4. Obviously, it's not going to be easy to put. This is the 60th, 59th, 58th, first, second, third, right? Okay. Now, so this is going to be a very long, this is called long polynomial. What's a polynomial? Polynomial is a long expression, right, with many terms. But it's got 60 terms. So, and obviously this is not, you cannot put everything. So usually, you use, ellipsis, right? Ellipsis means, you're truncating it, dot, dot, dot. But there's a better way of doing this, because this is obviously, not very smart. It takes too much time still. So what I would do is I would use sigma, the summation sign. Summation sign means, okay, that means you're summing up all payment times 1 plus r raised to n, where n runs from 0 to 59. Okay? Think about it. If n is 0, if n is 0, you put 0 there. Anything raised to 0 is what? Anything raised to 0 is, anyone? Anything raised to 0. What?
0.
No. Anything raised to
1.
0? 1. Yes. Who said 1?
Dennis.
Dennis. Okay, Dennis, you get 0.5. Anything raised to 0 is 1. I showed you an example, right? X squared times x raised to negative 2, right? And then that's, x squared times 1 over x squared, right? Which is, they cancel out. So it becomes x to 0, which is, x. So it's x squared over x squared, which, 1. Anything raised to 0 is. So if n is 0, then the whole thing becomes, if n is 0, the whole thing becomes just payment. If n is 59, right? If n is 1, then it becomes this. If n is 2, it becomes this. If n is 59, it becomes this, right? So this is a truncated expression that can capture everything. But then this is not a formula. In other words, this doesn't help you actually calculate it. This doesn't really help you actually calculate it, right? This is only an expression. But actually think about it. If you want to calculate it, you really have to, in other words, you enter $800 here times, you'll have to do 1.005. Why? 6% divided by 12 is 0.5%, right? If you do it like this, you'll have to do 800 first 800 when n is 0, 800 plus then 800 times 1.005 plus 800 times 1.005 squared, and you have to do it 60 of them because there are 60 terms, 60 of them. Then it's crazy. I mean, you can't. So we need a reduced form of this, and the reduced form formula. In other words, so future value of annuity, which is basically sum of everything, and running from 0 to t minus 1. Uppercase T means, a terminal time, the maturity, right? So we know if t is 60, we don't go all the way to 60, 59. The payment times 1 plus r raised to n. So when n is 0, when n is t minus 1, when n is 1, when is 2, n is 3, we have all 60 terms, or t minus 1, t terms there. 60. You might wonder, isn't it 59 terms because t minus 1 is 59? T minus 1 is 59, but we are even counting 0. I mean, when n is 0. 0 to 59, that's 60 terms. Now, reduced form is like this. Payment times 1 plus r raised to n minus 1, right? Close parenthesis, over r. This is the reduced form. So in other words, in our example, we'll be doing 800 times 1.005 raised to 60. In this case, n is actually 60 minus 1, because actually there are 60 terms. Minus 1 over 0.005. And I will show you how this formula is derived. Of course, once again, the step-by-step derivation, if you understand it and if you can replicate that process, then wonderful. You're a math guy. You are born for it. But at least I don't expect that. But at least if you can, understand. The important thing is this formula didn't just fall from the sky. This formula just didn't fall from the sky. It went through the steps of derivation, and it's important that you know that, you understand that it just didn't drop from the sky, right? So here, applying that formula, right? So here's the where is and go back to Excel. So now we go to, you see bottom tab here, multiple cash flow. Click that bottom tab, multiple cash flow, and then go all the way up. Oh no, I have okay. It looks like I have a view. I'm gonna have to I'll have to unfreeze pane. Unfreeze. Okay, I think now I can go on. All right. So do you see this? Do you have this in front of you? I want you to and I'm sure it must have been, it's blank. It should be blank.
Right. Yeah, it's blank, Professor. No
Okay,
data.
good. If it is blank, good. So now let's take a look at this. This is exactly our example. Your deposit or payment is $800. APR 8%. Your timeline 5 years, but compounding frequency is 12. Monthly compounding. That means you're making monthly deposit of $800 for 5 years. 60 deposits. So first we will have to find, oh, why is it jumping there? Come on. Here, I'm doing it here. Why isn't it showing equal sign? I don't understand. Yeah, I'm in E2, equal sign. I put equal there. I don't know why it isn't showing, but I put in, maybe because let me undo. Okay, let's delete contents, delete contents. Okay, equal sign. I put equal sign, but it's not showing. But let's see. I trust in E2 there is equal sign. And then it's simple. 6% divided by 12. It's gonna have to give you 0.5, right? Okay, so it's not showing the formula, but I don't know why. And then n as actual number of compounding, there will be 60 because it's 5 years times 12 months, 60. Now, future value of annuity, the formula is payment times open parenthesis, open another parenthesis, 1 plus. So pay attention to this because I don't know why it isn't showing here. R raised to 60 minus 1, close parenthesis, okay, divided by R. And hit enter. What does it come to? It comes to 55,816. 816. I'm sorry, 816. Now, some of you may say, hooray, I got it. No, not too soon. Why? This is just the future value of all those, $800. But we have a target future value. Don't forget. Right? What is our target future value? Anyone remember? What is our target future value? Why are we doing this? Why are we saving $800 every month for 5 years? Anyone? You forgot already. What is the example? What is the scenario of the example? What's the narrative? You are doing this. You are doing this for
college, for school.
Graduate school, not just college. Graduate school, right? You're right. You're doing it. And who was that?
Shirley.
Who was that?
Shirley.
Huh?
Shirley.
Shirley. At least one person remembers the scenario. Shirley, you got 0.5. One person remembers why we are doing this. So you are saving money for your graduate school fund, right? So you have a target future value. And what was the target future value?
50K.
You remember? No, 60K, 60K.
Oh yeah,
right?
Graduate school was 60K. You said the lesson school was 50.
Right. Graduate, CUNY graduate, 60K. And who was this?
Dennis.
I will still give you 0.5, but at least it's just input data, but you still remember the story, the whole narrative. So the question is, did we reach our goal? Can we reach our goal? We need 60K, but of course, we fall short. We fall short by about $4,000, right? So then what do? We can evaluate different other options or different strategies. Um, one option is increase your monthly deposit to 850. And what's it going to be? Second option is uh, find a bank that pays much better interest. But again, uh, 8% interest, let's try that. But reality is banking is a very competitive industry. It's really hard to find. I mean, all of them would be somewhere around 6%, right? A little bit above 6%, but nobody will be paying you like superior rate, like 2% more. Let's say it's possible to find one like that. Another option is, well, you extend your timeline to 6 years. You can you can postpone it by 1 year, and if that's the case, all right, you don't need to evaluate one by one. You can evaluate all these different scenarios or different strategies or different options all in a single shot, and that's the beauty of Excel. That's the beauty of Excel, right? We know by copying and dragging it down, we can compare it in a single shot. Okay, this may not be a that bad idea, increasing monthly deposit by $50, because we are close, but still we're still about $700 short. So we are very close. I mean, that gives us an idea. Oh, maybe $10 more, 860 maybe. Then we'll get there. But even if you find a bank that pays better interest, like 8%, still we are still short, about $1,300 short, $1,200 short. Um, if we extend it to 6 years, now we can, right? We easily overshoot. Our target. But we have $9,000 more, right? For by postponing our graduate school by 1 year, you get $9,000 more. We save 9,000. And with $9,000, you can probably get a good computer. You can buy a good computer and probably pay for uh, something else. I need personal transportation, so buy a good electric bike or electric scooter or whatever. Uh, you know, um, Again, the point is then, is there a way we can exactly nail the monthly deposit to exactly nail 60K? Yes, there's a way. Of course, I'm gonna get to that later, but not today because we are already. Now, what is this? This is called future value of annuity due. What is annuity due? So remember this in this example, um, this one is called ordinary annuity. You make the deposit at the end of every period. That's ordinary annuity. This is called annuity due. Annuity due is making the deposit or payment at the beginning of each period. And the, there will be a difference because um, there was one more. So what is the difference between annuity due and ordinary annuity? Um, of course, if I ask this question, some students always say, "Oh, annuity due, you make the payment at the beginning, ordinary annuity at the end." Oh, that's just verbal definition. Uh, but mathematical difference. What is the mathematical difference? Mathematical difference is that um, annuity due has one more compounding than ordinary annuity. Now think about it. If there was, if there was no, if this was, think about it. If this was ordinary annuity, it will start from here, and then the first deposit will be compounded 4 times, second deposit 3 times. But because the deposit starts at the beginning, first deposit gets compounded 5 times, second deposit 4 times. So what do you see here? First deposit gets every deposit gets compounded one more time than ordinary annuity. Isn't it right? So then, aha. I mean, clever person, there is an epiphany, moment of epiphany. I mean, great enlightenment. You get, oh, then I can, because the only difference is one more compounding. Everything. Oh, so if I compound this one more time, I mean, I can recycle this result. I can recycle the result of the ordinary annuity. So what I do is, I will multiply this by 1 plus r. That's basically giving it one more compounding. Giving it one more compounding. Then, there you go. That's the future value of annuity due. You drag it down. That's the future. Slightly better, right? You're not really, it's not that you cannot close the gap, but still much better, right? But this is how you calculate the future value of annuity. All right, so that's all the time we have. That's all the time we have. So if you have any questions, but was there anyone? I believe there was someone booked for today's office hour. So if you want office hour with me today, instantaneously, I can't do that. You will need to schedule, because someone is already booked today. Today's office hour is already booked with someone, so I cannot. So if you have any question, then email me or email to schedule an appointment. Okay, so that's it. Yeah, Said, you have a question,
Yeah,
Said?
Professor, I have a question. Are you still grading the homework? And when you're finished, are we gonna get like a
Professor?
feedback?
Yeah, I will return the graded homeworks. I haven't got started.
Okay.
I will use the weekend to do it. Okay?
Okay. All right.
Yeah. So okay. If you have any further questions, please email that to me. Yeah, Tatiana, Tatiana, Tatiana. I can't hear you.
Yes, Professor. Hello?
Yeah. Go ahead,
Can you hear me
Tatiana.
now?
Yeah, I can hear you.
Yes. I've been submitting emails to you. I have
Yeah,
not got no response
I
back.
got it.
I'm
No,
trying to inform you.
look, I've responded to you. Why don't you check your email? Right, Tatiana. There were
Hello?
here.
Hello?
Hello. Yeah.
Yeah, I have not
Tatiana.
received yet. Can you? I
No,
have not
no. Check.
received.
I replied to you. Okay.
I don't have
Um.
any
Oh.
reply.
Okay. So look, I got it. And was there any particular request? If there was any particular request,
No,
yeah,
it's just that
no,
I'm
listen. I took notice. Okay, and I just didn't have.
okay.
If there was any particular request, I didn't have time to reply. And if there was an urgent
Okay, no
request, I
problem.
would reply. Okay, but I took note. I took notice. Okay. Alrighty. So
Okay.
if any further question, please email me. I'll have to stop recording and get to my. All right. Take care. Stop recording and